Welcome to Higher Structure Seminar Series. Today, our speaker is Shannon Rubin from Yale Mathematical Sciences Center of Tsinghua University, Beijing, and he will tell us about homotopical invariant of Weinstein surfaces. We take Shannon Rubin for delivering this talk. So please, Shannon. Yeah.
Okay. Thank you very much, Professor Ikeda, for the invitation. It's a real pleasure to talk to all of you here. This is the first time I've given a research seminar talk online, actually, so it's a real honor to share it with many people. So the research paper is about constructing a certain DG category, which is supposed to be an invariant of ideally Weinstein manifolds in general, which are a certain type of symplectic manifold. But it turns out to be very complicated to analyze the singularities in general. So this research program was started just for the case of two-dimensional Weinstein manifolds, which are very easy to get a handle on. So the first thing I'll do is I'll describe what these geometric structures are to begin with, and then slowly get more and more combinatorial to end up describing the structure of a Weinstein surface completely combinatorially, and then go from there onto what the definition of this categorical invariant is. And then hopefully at the end, I'll have time to show you a couple examples of what it looks like. It ends up being quite simple to write down examples. But along the way, there's a couple interesting results that are just totally about homotopical ways to calculate limits of DG categories. And so that was something that's in addition to this, that was a tool that I used. So I wanted to share that with you as well. Okay, so I'll get started with just a brief idea of what a Weinstein manifold is. It's a certain type of symplectic manifold that has some good dynamical features. So here's what it is, a Weinstein manifold. There are many different definitions in use, and I'll give one that Laura Starkston uses because it's a couple of her results that I'm relying on. So Weinstein manifold is an open, exact symplectic manifold. So that means it's a even dimensional manifold with a one form whose differential yields a symplectic two form. So that's a non-degenerate closed two form. Such that so since there's a one form and a two form, there's a dual to the one form. The omega dual of lambda, which is a vector field V, is what's called the technical condition called Morse-Bot star, but I'll give an idea for what this means. In particular, this means that V should be roughly the gradient of some, maybe a Morse function, maybe more generally a Morse-Bot function, meaning a function that's allowed to have critical zeros along some submanifold. Not just isolated critical zeros, and it's a little more general than that. But you should think it's either a Morse function, or for my purposes, it'll be something like a Morse-Bot function. And then this condition that V actually is gradient-like. For a function. Gradient-like means with respect to some Riemannian metric, V is roughly the gradient of a function, but the function very rarely enters into play here. It's just kind of an idea that I'm going to reference a little bit. But the main point is that we have a vector field that has some good properties. And the usual way to understand the Weinstein manifold is through its skeleton, which is a retract of the manifold onto some interesting singular Lagrangian. A Lagrangian being a submanifold, which is half the dimension of the original manifold, and along which the symplectic form vanishes, which in the case of a surface is just any curve, is a Lagrangian. And in particular, Weinstein manifolds should be able to be understood by their skeleton. So the skeleton of a Weinstein manifold is defined to be this. It's all points in W such that the limit as you flow through t, so vt is the flow of t, of x exists. And so let me give a very useful example for me. So the example is this is going to be the skeleton of the manifold. Well, let me indicate it in parts, actually. If I'm thinking of having a function phi, which is gradient-like for a vector field, then these are going to be my index 0 critical points. Remember, I want to think of phi as being a Morse-Bot function, so it can have a whole manifold's worth of critical points. In particular, this means that the stable manifold of each of these points is just themselves. There's no points on the manifold that flow into these points. And then this one will be an index 1 critical point. And being an index 1 critical point, that means that there's going to be a whole 1 dimension's worth of points which flow into that point via the flow of t. So I'm going to indicate that using this. This will be the stable manifold of t. I'm sorry, the stable manifold of that critical point. And then altogether, this is the skeleton. So altogether, this singular one-dimensional thing is the skeleton of the manifold. And what is the manifold? When I draw a picture like this, the manifold itself is just an arbitrary neighborhood in the plane of the skeleton. So this is the manifold. And any other point that's not on the skeleton will move via the flow to some point on the open boundary. It's an open manifold, so there is no boundary. And so only these points have a limit which exists. Okay, and so this is going to be a good example for me, because now I can basically understand the manifold just by its skeleton. And I want to make the skeleton very combinatorial so that it can be more amenable to drawing, say, diagrams of algebraic things on it. Okay. So, in particular, these two pieces right here that I drew, this index 0 piece and this index 1 piece, these are referred to as bones. Bones of the skeleton. And in some degenerate cases, the skeleton may not be able to be broken up very nicely into bones or whatnot, or sometimes the bones might be badly behaved. They might not necessarily themselves be Lagrangian submanifolds. But what kind of underpins a lot of this work is this result by Starkston, that every Weinstein manifold is close to one which can be described via this bone way. So I haven't exactly said what a bone is, but you should imagine it's like this collection of stable manifolds of certain indexed critical points. In one dimension, these are really the only two kinds of things that show up, this line of zeros or a stable manifold of an index 1 critical point. So Starkston says every Weinstein manifold is homotopic. So this is a technical word for Weinstein manifold, Weinstein homotopic. It just means that there's a one-parameter family of Weinstein manifolds that from start to finish. And there's maybe some technical analytic conditions there, but it basically means it's a one-parameter family of Weinstein manifolds. So like an isotopy through Weinstein structures, more or less. Every Weinstein manifold is homotopic to one whose skeleton is built of bones. And again, I haven't said exactly what the technical condition is, mostly because this is all kind of motivation for the algebraic work that I'll talk about later. But this is kind of the idea. Furthermore, I noticed that these bones have very nice local structure here. They really just form this kind of trivalent graph, and that's the only kind of singularity that appears. And that's what I want to talk about next, is the presence of singularities in the skeleton and how to make sense of them. For example, we could have a situation where we had a maybe something like this, where it's not trivalent, but this is going to be homotopic to one that is trivalent, and that's what I'm going to say next.
Sorry,
So this is going to
can I
be
ask something?
yes, of course.
So the one that you just draw through and
Yes, I erased
erase,
it.
right?
Yes,
Is this now bone or not bone? I mean, I get confused about the definition. Is this a
yes, yes. This is still a legitimate Weinstein manifold. The um the the Lyapunov
is
function,
this
I think, is more spot, or if it's not more spot, at the very least, V is still more spot star. This is totally legit. And the stable manifold of this critical point just happens to look like this.
this is also made of bones? Is this correct or no?
Yes, yes, this is made of bones. Yes, it's just not arboreal, which is what we'll do next. Yes.
But what is not made of bones? Then I couldn't think of an other
Well, something
skeleton
that's
which
not
is
made of
not.
bones. It might not even be possible in two dimensions. I'm not quite sure exactly what something not made of bones would look like. That's a
So
good
it's
question.
not
I
a
think,
not
yeah,
a
I'm not
trivial
sure
thing
exactly.
to think.
I
See.
think I'd have to look like into the analysis in Laura's paper. Um, yeah, I can
Okay. So
easily
this is
draw something that's
this.
not arboreal, but I think something that's not made of bones is kind of complicated. Yeah.
I see. So this statement is for any dimension. It starts off.
Yeah, this is true at every dimension. Yep.
Okay. Okay.
Right. So, yes, now let's talk about the singularities that could possibly appear. And this is the big program of arboreal singularities. So, the story is that Maxim Kontsevich started to think about what possible singularities could occur in Weinstein's skeleta. He gave a list of a few that, an infinite list that he imagined might be a good representation. David Nadler then extended this list to more, and David Nadler's singularities are these so-called arboreal singularities. So here are what they are, and they're indexed by rooted trees. So for every rooted tree, so a rooted tree is a tree with a selected root row, which is one of the vertices. That's all a rooted tree is. For every rooted tree, call this curly T. It's not a good curly T. Say with n vertices, always a finite tree. There we go. For every rooted tree, a singular Lagrangian. In the symplectic manifold T star R n minus 1. And so let me just list out the first few of them, just because they're interesting to see. So here will be the rooted tree, and here will be the singular Lagrangian. So here are the first few rooted trees, just a dot. Here's another one, and there's two rooted trees that have three vertices. And the associated Lagrangians look like this. So this would be just a point in the line. Oh, I'm sorry. This is just in 0 dimensions. So this is a point in just the point. That's not very interesting. This one is the one that I'll use over and over. This is a singular Lagrangian, which is a one-dimensional Lagrangian in the plane. And then the other ones can't be drawn, at least as Lagrangians, but their projections can be drawn. So this would be a two-dimensional singular Lagrangian in R4, but we can look at its projection in R3. And it looks like this. And then this one is a little less symmetric. It's a full plane, a half plane, and then a quarter plane. Okay, but actually the only one I need is this one right here, and I guess technically this one too. But the point is, in two dimensions, there's only this one trivalent graph. And Nadler thought, okay, maybe we could use all of these as local singularities to model all Weinstein manifolds. That was kind of the idea. It's known now that in high dimensions it's not quite true, but in the dimensions that I care about, it will be true. And Nadler's main result here was to classify the microlocal sheaf categories associated to each of these arboreal singularities. And I won't need anything about microlocal sheaf categories, but they're just supposed to be a reasonable symplectic invariant of Weinstein surfaces to associate to Weinstein surface a full subcategory of its sheaves, which is microlocally supported in whatever that means along its skeleton. And these are also supposed to be kind of a sheaf version of the more analytical defined Fukaya category of a symplectic manifold. So this is kind of where Nadler's operating from. The idea is that this sheaf category associated to this Lagrangian, and each of these Lagrangians can also be thought of as a Legendrian in a contact manifold, a contact boundary of T star Rn minus 1. So brushing over that detail, because that's really where microlocal sheaf categories are defined. If I take this contact manifold, S star of Rn, this is the sphere bundle, cotangent sphere bundle, and think of LT as a Legendrian inside that, there's a usual meaning for what a microlocally supported sheaf is. So this is the category of sheaves with microlocal support, mu support, along. So it only changes along these particular directions. But in any case, the point that matters for me is that he showed this is equivalent to maybe a derived DG category of modules over the rooted tree. So the rooted tree can itself be thought of as, directed. So then you can get diagrams of DG modules over this. And this is where I'm going to be focusing. In particular, Starkston showed that in dimensions 2 and 4, all Weinstein manifolds are homotopic to ones with only arboreal singularities. In the skeleton. So this justifies kind of the work that I'm going to do from here on. If I only look at arboreal skeleta that are built of bones, that really does capture all Weinstein surfaces. And the same program should work for 4 dimensions. I don't yet know how to do it, but the same idea should kind of go through as long as one kind of pays attention to all the singularities. One's guaranteed that this will apply for all Weinstein manifolds in that dimension because of this result. Okay, so that was kind of the background of the geometric story. I'm now going to focus in on the combinatorial aspects of assigning an invariant, because now by these theorems of Starkston, I can focus completely just on arboreal skeleta, just basically trivalent graphs. Okay, and so the first step in that direction is this. Any two, so I'm going to call these arboreal surfaces. So when I say arboreal surface, I just mean a Weinstein surface that has arboreal singularities along its skeleton. So any two arboreal surfaces are homotopic, if and only if related by these sequence of moves. And these are very kind of obvious moves that one would do to a skeleton, at least from the perspective of Morse theory. So let me just draw them out. So these are all performed locally. So what I mean by locally is when I don't put a dot here, I mean that these go on like this. So this is just a local description, and this will modify to be an isotopy where I move this around. This doesn't happen for Morse functions because Morse functions just have single critical points at index 0 critical points. So there's nothing to isotope around. So this is kind of an additional thing in addition to Morse theory. In addition, there's another one that has the exact same situation. I just move these two past each other. And I guess I should be clear here. When I draw something horizontal, I mean that to be an index 0 bone. When I draw something vertical, I mean that to be the stable manifold of an index 1 point, what I was calling an index 1 bone. So always the vertical ones will be those index 1s, and the horizontal ones will be the index 0s. In practice, it makes very little difference, but that's the way that I'm drawing them. Anyway, these two are isotopies, and then the other two come directly from Morse theory. One of them is a birth-death cancellation of critical points. So it looks like this. So here we have a index 0 critical point and an index 1 critical point, and I just cancel both of them. And I'm just left with this other piece. And that comes straight from Morse theory. And then the last piece is the handle slide of Morse theory. So I'm sliding one index 1 handle over another onto a different index 0 cell. Okay, so the idea is going to be, if I want to assign some invariant of Weinstein surfaces, it's good enough to just define one which is invariant under these 4 moves. So only 4 moves have to be checked to define an invariant of Weinstein surfaces. Okay.
Can I quickly add something
Of course.
about the first one? Did you deliberately not put dot for in the
No, I did
first
not
one?
deliberately. No, they are the dot dot dots are right here.
I mean, which one? Not that one. I mean, before that one, the
Uh,
first picture.
yes, here they are.
So in the top left one, there's a no dot at the
Right, right. This is the end. Yeah, you can isotope around the end of a 0 bone.
so it's deliberately not. It's
Yes,
really
I think
ambiguous. Okay,
all the dot dot dots are in there now.
okay.
Yeah, yeah, exactly.
Okay,
You only
thanks.
isotope around the end of a 0 bone.
I see. Okay, thanks.
But of course, using handle slides and all the rest, you can take any one bone and you can move it around anywhere you want. So you can move around an entire 0 bone.
I see. Okay.
Mm-hmm. Okay, so here's what the invariance is going to be. Um, First of all, in dimension 2, we only have these two trees that come up. We have mod, so DG modules over just a point. This is going to be chain complexes on here. K could be any commutative ring. So chain complexes on the ring being used for the base of the DG categories, and then mod of the A2 quiver is just chain maps. So this is chain maps. More generally, actually, none of what I'm going to do has really anything to do with chain complexes at all. So more generally, I could just instead do the following, just fix anything that kind of behaves like the category of chain complexes. So fix a pre-triangulated DG category A, and I was only able to grade things over Z mod 2. I think there's a real obstruction to grading over Z. So in particular, I should emphasize these are Z mod 2 graded DG categories. But Yeah, you can think of the category of chain complexes, but never are we going to need to like actually reference that. And I should also emphasize that when I write something like, instead of calling this arrow, let me just put the 2 here to indicate that it's, functors from the arrow category. In particular, A2 is, it's not strict modules. These are more specifically A infinity functors. Let me just say more carefully what this category is. It has objects, arrows, closed arrows in A, and it has, let me just say what the closed morphisms are. The closed morphisms from, say, one arrow A to another arrow B. A closed morphism would be something not quite a commutative square, but a homotopy commutative square. So that's what a closed morphism is between two objects of A. A2 is a homotopy commutative square, meaning a map whose differential is the difference of the two paths. Okay. So here's what the definition of the invariant is. It's going to take a skeleton, which we might as well just think of as a trivalent graph, and map it to a diagram of DG categories called L of, let me say W. W was associated to the skeleton. And then I'm going to take the homotopy limit of this. So it's going to be the homotopy limit in the category of DG categories of some diagram. And when I say homotopy limit, this has to be with respect to some weak equivalences. The weak equivalences are quasi-equivalences of DG categories. So this can be computed with respect to, say, the Tabawada model structure on DG categories. The trick, though, is that even though there's a nice model structure on DG categories, you never get from that a nice model structure on diagrams. And that's kind of what a lot of the crux of this work was, trying to understand model structures on the category of diagrams in order to compute homotopy limits. And that's what I'll talk about later. But here's what the invariant is. I'll just describe what the construction of L of W is. So here's what it does. It takes to any... sorry, my pen is glitching a little bit. Okay. It takes any edge in the trivalent graph, and now this edge can be, it could be a 1 bone or a 0 bone. At this point, everything is just a graph. And it associates to that the following diagram. So I'm going to take the category A2 and associate it to both vertices, and the category A and associate it to the edge, and then some arrows, some functors between them. And I'll say what those functors are in a second by describing what they are locally at every vertex. So every vertex is trivalent, and that trivalent vertex is going to be sent to the following diagram. Right, so every vertex is supposed to map to the corresponding edge, and the diagram is very simple. There's really only 3 things you could do with a general, say, chain map. You could take its domain, you could take its codomain, or you could take its mapping cone. And that's why I needed A to be a pre-triangulated DG category. Or if you want to say it's just category of chain complexes, you can take its mapping cone there. So that's what that does at a vertex. Of course, there's also these univalent vertices, and those are very simple. Those just get sent to 0. And then one last ingredient is that some of the arrows here need to be shifted, so possibly shifted by something, and I want to now give a prescription for how exactly to shift some of these arrows. So it's going to look like this. I'm going to draw kind of a picture next, and the picture I'm going to draw has some of the edges marked with a slash. Those edges which are marked with a slash are going to follow the following procedure, that you compose one of the arrows, one of these arrows right here, compose one of those with one shift. Okay? It turns out it doesn't matter which of those arrows are composed with a shift because of the Z2 graded nature. So just compose one of them with a shift. And once I say exactly which of these edges get marked and get that shift, that will then uniquely define what L of W is. Okay? Let me give a quick example before I actually give the rule for the marking. So for example, I think we already looked at this. We already looked at this graph here. So say I give you this graph and say I give this one to have a marking. It's going to turn out that the rule will assign a marking to that one. So what will this correspond to? Under this description, it says, to every vertex, I give an A2, except for the univalent ones, they get a 0. And then to every edge gets an A. Remember, A stands for any pre-triangulated DG category, or if you like, just the category of chain complexes. And then I just draw the arrows according to what the graph looks like. And I can label them with what they are, but it's easy to remember because it always goes kind of in a counterclockwise way. I take the domain, the codomain, and the cone. And here I take the domain, the codomain, and then this one I'll choose to shift by 1. So like that. Okay? So that'll be the rule for that. Let me just now say what the rule is for the markings. Okay. So here's the rule. Let me give a suggestive picture that basically will explain the rule without having to say too much. It looks like this. Suppose I have these 0 bones going on here. And suppose I have some of these 1 bones. Maybe they look like this. It doesn't have to be a planar graph. They can go past each other. Maybe like that. Maybe one goes around like this. So that's kind of a generic picture for what these things can look like. Maybe this one goes on the, there's one more on the bottom. And the markings are going to be as such. Basically, any of the 1 bones that sit either completely on the top or completely on the bottom, those are going to get marked. So this one gets marked, and this one gets marked, and this one gets marked, and that's it. So only the 1 bones get marked, so only the cones get shifted, the cone functors, and only those that sit either on the top or bottom get marked. There's a little bit of a subtlety because I chose to embed this graph in the plane in order to tell you what's on the top or the bottom, and so that has to be addressed. So here's what the real rule is. So orient, this is where the embedding is going to come in, orient all 0 bones. So those are these guys right here. And then mark all 1 bones, or mark a given 1 bone, mark a 1 bone, and remember these are these things. If and only if both of its so-called joints, or its feet, its endpoints, both of its endpoints are on the same side. Right? So when I draw a picture like this, I'm always going to assume that I've oriented the one bone or the zero bones from left to right. And then you can see that, this foot is on the, if I'm moving along the zero bone, this is on the left side of the arrow. Or if you're drawing the arrow from left to right, it's on the up. And so is this one, whereas say these are on opposite sides. But it technically does require this orientation of the zero bones in order to make this, precise and not just rely on some arbitrary embedding into a plane. So this is an auxiliary choice right here. The rule does depend on this orientation of the zero bones. So I haven't quite precisely defined what L of W is, and I'm not going to because the homotopy limit is invariant with respect to this auxiliary choice. So that's a lemma, that the homotopy limit is independent of the choice of orientations. Okay, so that says, okay, L of W is not fully well defined, but the homotopy limit is well defined. And of course, when I say well defined, I mean in the only sense in which the homotopy limit is defined at all, which is up to weak equivalence, which is quasi-equivalence of DG categories. And then here's the theorem. So this says that homotopy, that the invariant is well defined. Then the next thing is to say that it actually is an invariant. So this is invariant under Weinstein homotopy. Right, so invariant means up to quasi-equivalence, and Weinstein homotopy is really just captured by those four moves. So this is proven just by checking that the definition is invariant under the four moves. And so I won't go into detail about it, but basically each move can be broken down into smaller pieces, and it can be said exactly how those pieces affect the definition of L of W, and then show that those changes are independent. That the homotopy limit is independent of those changes. To do this, to show these pieces, required having a very concrete formula for what the homotopy limit is. In Duan's thesis, he gave a very nice formula for the case when the homotopy limit was a pullback, a homotopy pullback. He gave a formula for DG categories, what to do, and I wanted to use that formula, but for more general pictures, not just pullbacks, but for these more general diagrams that have, like this one right here. In particular, notice that that this diagram really actually is a collection of pullbacks. It's just four pullbacks glued together, and in fact, that's always the case. Every edge in the original graph corresponds to a pullback. So that's what I wanted to exploit, and the next part of this that I'm going to talk about is the way to prove that this general formula for calculating pullbacks will work in the more general case where I have many pullbacks, and it's a little bit more complicated because there's kind of there's like when I glue multiple pullbacks together, there's like some monodromy going on in the middle there. And so that's the next thing that I want to talk about. And it's no longer related to DG categories or Weinstein surfaces at all. It's just a result about how to compute homotopy pullbacks or more general homotopy limits. So are there any questions about the pictures here, the Weinstein manifolds, before I do that?
I have a question about marking.
Yes.
Maybe I misunderstood, but if they are same side, if the ends of one bone are the same side, you mark them, right?
Yes.
But why then
Oh,
the
so
one at the bottom is not marked?
thank you very much.
Okay, it's supposed to be marked.
I'm sorry if
Okay.
that caused any distress.
It's okay. Thanks.
Thank you. Okay, so here's kind of the model category part of the story, that we noticed that locally we just had L of W. So let me just say this. So locally, L of W was a pullback. With respect to some functors. Let me call this diagram D. And it's not too much work to show that the homotopy limit of D is given by the limit. This is kind of very common formula in, say, algebraic topology, or it works for many model categories, but in TG categories, it can be shown easily. I saw this in Doan's thesis, that we can kind of fatten up this diagram by replacing the middle A with this subdiagram of taking the path space of A, or path category. Where this path category is, it's the full subcategory of maps consisting of the homotopy equivalences. So those maps in A which have an inverse up to homotopy, or which have an inverse up to, like, modulo exact maps. So that's what the paths are in A. You kind of just basically you just take the groupoid that's inside A2, and those are the paths. And so this gives a really nice formula. Normally the pullback here would be like all possible pairs of maps which are exactly equal. F of one equals exactly G of the other. That's kind of not really good, homotopically speaking. The homotopy limit says, well, it's really just a map here and a map here, such that F of the first map is not equal to G of the second map, but they're related by a homotopy equivalence. And the homotopy equivalence is part of the data. And so what I want to say is that basically the same formula works in the more general case, but it took me quite a bit of excursion into model stuff to prove. Okay, so more generally, what I want to say is this. Globally, let's take L of W and replace it by this kind of path extension here. So I'm going to call that path of L of W. So when I write path of L of W, all I really mean is that I've taken every pullback and I've replaced that with this picture here, where it's the path category that's in the middle. Okay? And then the main result that allowed me to actually get a handle on calculating stuff is, first of all, that the homotopy limit of L of W is unchanged by this. Sorry, that this is the homotopy limit of the path extension. Okay, this was not too hard. This is kind of formal, abstract stuff, just properties of homotopy limits. What was a little bit more work is showing that this homotopy limit is actually just a regular limit, and this is kind of the result that's needed, right? Because that's what's being said right here. Okay, so this is the part that was interesting. This one needs some work. And so it's this last result here that I'm going to describe kind of where it came from. So I'm kind of working backwards from the main theorem to kind of all the tools that were used to find it, because I think it's not very interesting in the forward direction. Okay, so here's how it goes. What really happened in the passage from L of W to path L of W was really, we started with, say, a graph. A graph G. And at every edge of G, we replaced it by a quiver Q of G, right? And then we had that that the original diagram L of W was defined on on Q of G. For example, we had this one, this G, and we have that path L of W, right? By definition, this is extending every piece like this. This one was defined on Q of, say, like the subdivision of G. So when I say the subdivision, I really just mean you take every edge and you just add an extra vertex there, right? That's really what happened. This is sub of G. So I just wanted to kind of see that, so we can see kind of the relationship between the shapes of these two diagrams. Okay, I'll put that aside for a second. We'll get to it later, but I'll just give the main technical theorem that was used to show that this path diagram, its homotopy limit equals its own limit. Basically, it's kind of like a projective object in the category of diagrams. Its derived functor of it is just equal to the original functor of it, where homotopy limit is the derived functor of limit. So here's the technical result. The idea was that we have this new kind of shape, this quiver, and it's a very simple quiver in the sense that no two arrows are composable. It's just a quiver that's composed of a bunch of pullbacks everywhere, right? So there should be good model structures on the category of diagrams over this quiver. In particular, whenever you have a nice quiver, you can put what are called a reedy structure on the quiver. A reedy structure is like a very combinatorial way to describe which arrows kind of increase a filtration on the quiver, and you kind of define things inductively based on this filtration. But in particular, one thing a reedy structure can do is, if you have a reedy structure on your quiver, it automatically induces a model structure on diagrams, if those diagrams take values in a given model category. But you get a different model structure for different reedy structures. And this is very useful because different model structures on the category of diagrams might be more useful than others in order to classify what the, say, projective, the fibrant diagrams are. And so what I did is I classified all of the reedy model structures which are useful for this purpose of proving that the homotopy limit equals the limit. So here's the technical statement. Let M be a model category with all objects fibrant and all Cartesian projections, so I'll just say projections, are fibrations. I'll say I think this is kind of a unnecessary technical requirement. I think there's a way to get rid of this requirement at the cost of just making the statement of the theorem more complicated. I don't think it's an essential requirement, but in any case, I use it because it is satisfied by many model categories. In particular, DG categories does satisfy this, and some categories of spaces and chain complexes also do. But I don't think it's very essential. It's just the version that's useful right now. So let X be a diagram. So M with shape in the given quiver. Then the following are equivalent. So what it really is it's a bijection between reedy structures on the quiver and certain other kind of conditions on the graph itself, on the diagram X itself, I mean. So here's the first condition, that there exists a reedy structure on QG, such that now not any model structure is useful for the derived functor of homotopy limit, right? Usually when you need a model structure that has a good properties with respect to this functor, and here's what that property is, such that the limit functor the limit functor is a right adjoint to the constant functor, and so the right thing to ask for with a model structure is that this is right quilled, which is a technical condition. It means that it preserves, I think it means it preserves trivial fibrations. Such that this is right quillen, and of course we need X to be fibrant in this resulting model structure, such that this is right quillen, and X is fibrant. So I've already implicitly assumed that when I write this, I mean the induced model structure from the Reedy structure. So the Reedy structure induces a model structure on diagrams, and that's what I mean when I write right quillen, for example, and when I say fibrant. It's with respect to that induced model structure. Okay, so that's the first condition. In particular, this already implies what I need. Just general properties of model categories imply that this means that the homotopy limit of X is weakly equivalent to its own limit. But it's stronger than that. It's a more structural condition than just this one equation, which is why I'm stating it that way. And the second is an actual combinatorial thing that you can check on the diagram itself. So you don't have to actually... The idea is the first one is a structural kind of condition. The second one is the actual thing you check in order to show that it works. So there exists an acyclic orientation on the graph G such that for all vertices in G, a certain map is a fibration. So this map is, so X has a value at V, it's a diagram, and then I'm going to map to all possible, I'm going to take the product over all possible, some edges in a certain subset of edges in the quiver that I'll draw for you. And this subset is going to be called A of V, just to give it some name. And then I'm going to take X evaluated at the codomain of all of those edges. All of these edges will have domain V. So these are going to be edges out of V. So I'll say what those edges are. So I'll describe what this set AV is. And then the condition is that this is a fibration. In M, right? I don't have to refer to model structures on diagrams anymore. So just a fibration in M. Okay, so here's what that set AV is. So locally in G, V is a vertex, and it has some edges going in, and it has some edges going out. Of course, in our situation, all the graphs are trivalent, but this is more general. It doesn't require that at all. So in G, this is what happens locally at V. And what happens in Q of G? At Q of G, all of these edges are replaced by cospans, right? So all of them are replaced by, it doesn't even matter what direction these are for what Q of G looks like, right? This acyclic orientation is auxiliary. But these all are sub-pullbacks, and they always look like this in Q of G, right? So again, Q of G ignores what the acyclic orientation was on G, but A of V will select for it. So only those that went in are going to be selected in A of V. And so A of V is going to take together these three arrows. you can kind of see what the general definition would be. So this is the collection A of V of arrows. Only those arrows out of V, which originally came from arrows into V from G, from this acyclic orientation that I fixed on G. Okay, and so I just take those, so in this case I would just take those three arrows and I would take the product over those three arrows. And that would be this map that I want to be a fibration. In practice, usually very easy to check. Okay, so that's the definition, that's the theorem, that the following are equivalent. You just check these, check the second condition, and then you're automatically guaranteed in particular that the homotopy limit equals the limit. And then this can be applied very immediately for if I take the path extension of some diagram Y, so say Y lives in some M of Q, say G prime, Y is some diagram, and I take its path extension. This is going to live in M of Q of sub G prime. And this sub G prime is going to be the G in the theorem. And this will automatically satisfy the condition. So the path extension of any diagram satisfies the condition of this theorem. So this satisfies the theorem. Basically because the only thing that really has to be checked are these two maps. And these two maps together, when you make a product of them, they are a fibration. That's kind of, well, that's one of the properties that a path object is supposed to have. Tabawada is the one who proved, right? It was a short proof that these actually, the product of these two maps actually is a fibration, and that's really all that has to be checked in this particular instance. So the application of the theorem is very easy in this case, but I thought the theorem on its own was also kind of interesting. Okay, and that's basically the rundown of the whole proof of invariance, that I show that any path extension satisfies this condition, because this map, say, if I call this pi 1 and pi 2, the idea is that pi 1 cross pi 2 is a fibration. In any model category, actually. It doesn't have to be DG categories, but in particular, we can apply it, and that gets us to the result above. This one right here, and that's the proof of invariance. Sorry, that's the technical tool, this formula for the homotopy limit that allowed me to prove the invariance. I used this formula to then calculate things and show the invariance. I'm skipping that step, but that was the motivation for getting this formula. The formula was kind of necessary in order to prove the invariance. The invariance of L of W didn't just fall out kind of by abstract properties. Maybe there is a way to do it, but I kind of resorted to this more concrete tool. Okay, I'll just very quickly give you some very small examples of what the invariant is. So, in particular, on the case we've been looking at for a while, this can be, this diagram itself can be simplified to one that kind of looks like this. And then this kind of suggests that I should have one object. So L of W is just a single object, say, maybe an object A, maybe a chain complex, and then a single homotopy equivalence. Another example is if I take, so this would be a cylinder, annulus. Another example is I take 2. This can be modified like this. So this is a pair of pants. And the category turns out to be, there's a technical reason that I don't actually have to do a homotopy between all possible ways of identifying the, say, codomain and the domain. These would be two arrows corresponding to these vertices. So it turns out that this can be simplified a little bit. and I could just say it's I can identify one of their pieces. So a map F, let me call it like A, and a map G, and they can have the exact same domain and codomain matching up, and then they're going to be identified via a homotopy here. And then a condition on their cone, that the cone of F is equivalent to the cone of G shifted by 1. Okay, so that's another example. We could also do a torus or a punctured torus, and that would be a very similar kind of version. But in practice, the last thing that I'll write right here is just any genus surface can be very easily achieved by drawing something like this. So if this is 1, 2, up to G, this is genus G. And then if I draw a few more of these, one up to N, this is the number of punctures is either N plus 1 or N plus 2, depending on whether G is positive or 0. And then very similar kind of little descriptions of these can be written down in any of these cases, just kind of a collection of maps, and it turns out that I only need one homotopy in that cycle. All of them can be identified with domains and codomains except for one little homotopy, and then for each of these edges I need some condition on the cones, and it's not just a condition, it's data. The data of the homotopy is part of the object. And that's what the objects in these categories look like. Okay, that's the end of the talk. Thank you very much.
Thank you, Shannon. Thank you very much. Any questions or comments?
Can I ask a question?
Please,
Of course.
Ron.
So one question is maybe simple one. You said you take Z2 coefficient or Z2 graded complexes?
Good. Z2 graded complexes. So Z2 graded
Okay.
DG category, A, over any commutative unital ring.
Okay. It makes sense.
Yes.
And in your main theorem, or I don't know if it's your main theorem, but last theorem that you show, I didn't understand the acyclic orientation's role. I mean, what's the idea behind it? Why you needed to give
Okay.
such?
Well,
Is it like difficult to explain? I don't know.
like the definition of AV, or do you mean more kind of
No,
theoretically,
no,
like why, like where, like what the idea of why it had to appear?
yes, and why that grants you this equivalence between the first and second.
I don't think I have a
Uh,
great, I don't think I have a great like big picture understanding for why this happened. It was a very kind of like combinatorial calculation that the acyclic orientation on G allowed me to say exactly which arrows in Q should be the increasing arrows in the filtration on the Reedy structure.
ah,
I think it was maybe like given the acyclic orient, so every edge in G looks like this, and then every arrow in Q, all the arrows in Q look like this, and I think um, um, up to changing all of the signs, I might as well say that like I could start by assigning any arbitrary arrow direction to Q to this arrow in G, and then I could say that say this would be a plus arrow and this would be a minus arrow, say, if I've already assigned an arrow in G. And then I say, if the acyclic orientation agrees with the arbitrary one I already fixed, then that's the plus and minus I assigned to the arrows in Q. If the acyclic orientation disagrees with the auxiliary one I already fixed, then I use the minus and plus. And yeah, that's basically the bijection. Yeah, that's the bijection. If I remember correctly, that's the bijection between the Reedy structure and the acyclic orientation. And then I think one of the axioms of the Reedy structure exactly enforces that this orientation has to be acyclic. Oh, I think it's that like you can't have a cycle. Yes, this is it. You can't have a cycle of increasing arrows in a Reedy structure.
Then you will have 1 equals 0 kind of thing, right? Because it's increasing and it comes back to itself. That's right.
Yeah. So it was just like one of the parts that basically the definition of Reedy structure and the definition of fibrant in a Reedy model structure, which is a condition on the matching objects associated to X, and the condition of being right quiland, these all enforced these pieces on the other side of being an acyclic orientation. And basically the fact that this is a fibration is exactly saying that all of the matching objects of X are fibrant. So that's the definition of fibrant in a Reedy model category. And so checking that these matching objects are fibrant, I think was what got translated here into this being a fibration for these, and this was the translation of that. I could also say that this does not just apply to quivers that arise from graphs, but any quiver which is simple enough that it has no arrows which compose. So in particular, it could have like some sources or some sinks, but it doesn't necessarily have to arise from a graph in this way. Just any quiver that has no composable arrows, this theorem will apply to with a slight generalization of the condition 2, which is in the paper. But in the case of the quivers which arise from graphs, the description simplifies a little bit to look like this.
Yeah, your theorem seems like a very strong compared to what you want. So probably it will have more applications in other things because your case is very simple.
Exactly. Yeah. So it was kind of two separate things. There's the geometric thing with the Weinstein structure, and then this kind of more theoretical result on Reedy structures. And yeah, it's much more strong than is needed for the other case. Yeah. But in particular, it's not strong enough to work for 4-dimensional Weinstein manifolds because in those the relevant skeleton has arrows which compose. You can have a map from like a 0 cell to a 1 cell to a 2 cell. Yeah. So it's not good enough to work for any higher dimension Weinstein manifolds. Any other applications would have to be like something different. Yeah.
I see.
Yeah.
Any more questions or comments?
Thank you very much for this talk. I appreciated that.
Oh, I'm glad. Thank you.
Okay, so let's thank Shannon once more. Doğancan, you have one more question?
Sorry, can I ask before? I forgot to ask this question. I was curious. Then very quickly, you put this what you call slashes on the edges, right?
Yes. These
what's
give you this I'm sorry?
What if you don't put any of these slashes? Like what's
Yes,
happening?
so one thing that I didn't say is like kind of why these appear. They appear basically in the proof that when I do the slashes in particular have to do with the rule that assigns the isotopy. So this rule here in particular, the effect this has on the homotopy limit is exactly by shifting. So like the L of or the
I see.
yes the let me say the homotopy limit of this um, equals only the like if you didn't apply the slashes, it would only equal the homotopy limit of this if I add a +1 here.
I
And
see.
so
It's necessary there.
I need these markings so that when I move to like you see if I were to move this guy instead of being on the bottom, if I were to slide it so that it would be instead on the top, then it would have to get a slash in order for this correspondence to work. So that was it was necessary because this isotopy exactly flips
Yeah.
the yes.
Yeah, now it
And this
makes
is why
sense.
it had to be
That is,
Z2 graded, by the way, because it does it the same way when you go the other way. It keeps adding one.
true. That's
Yeah.
why I asked that to grade this photo because
Yeah, that was one reason it had to be
I
Z2
see.
graded. It was also because the handle slide also adds one, and then if you were to like handle slide back, you would want it to. I think it also adds one again, confusingly. Um,
Or in other places also there will be some inconsistencies if there's no Z2 graded, I think.
I'm sorry.
So there will be some inconsistencies if it's not Z2 graded,
Right, right.
but
Yes.
maybe not all graphs. I think some graphs may be okay, but I've
Oh,
I'm I
I'm not sure because
from
you can make these graphs very complicated using the moves. In particular, using the cancellation move, I can just add extra handles many times. Yeah, but maybe some graphs it's not necessary, but definitely I couldn't find any way to make it consistent Z-graded. I don't know whether it's possible or not.
it should be related to Chern class somehow.
Oh, yes,
Chern
I think
class
you've told me this
automatical.
before. Yes. Hmm.
But anyway, so maybe we already talked, so I can. But I understood your explanation.
No,
Thanks.
thank you. I'll keep it in mind. Yeah.
Okay, that's my all questions. Thank you.
Thank you very much, Shannon. So
Thank
it
you.
was a very nice talk. Uh, these are the results of your PhD thesis?
Yes.
Oh, I see. Very nice. So you are in China now, and uh, there are we have one more. We had one more speaker from Yao Institute, actually.
Oh,
Uh,
really? Who?
um, well, he works on higher categories, and well, what was his name? Uh, well, I will send email to you what his name is. I forgot. But
Okay. There's
yeah,
many postdocs here. We don't we don't all know each other, but maybe.
he's but probably a senior, more a bit more senior. He is tenured, I believe, there.
Oh, professor. Yes. Okay.
Yeah. So okay, so let's thank Shannon once more, and we will hopefully meet 2 weeks from now, and hope to see you then. So I stop the recording now.
Okay.